Tonight, we're going to look at one of the most ambitious ideas in all of science, the generation ship. It's a vessel built to cross the enormous distance between the stars, so large it works like a small world, and so slow that the journey takes centuries. A journey so long that no one who boards it will live to see the end, and the people who finally arrive will be distant descendants of the ones who left. It might be the only way our species ever travels to another star. But could one sealed ship really keep an entire population alive, fed, healthy, and stable for hundreds of years, with no resupply, no rescue, and no way back? By the end of tonight, you're going to understand exactly what it would take to keep a generation ship alive, what would slowly work against it, and how long one could realistically survive in deep space. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The nearest star beyond our own sun is Proxima Centauri. It sits roughly 25 trillion miles away from Earth. At the speed of Voyager 1, the fastest probe ever to leave the solar system, moving at 38,000 miles per hour. That journey takes approximately 70,000 years. And Proxima Centauri is the closest option we have. If you want a star with better odds of having a livable world, you are looking at systems that are 10, 20, 50, or even 100 light years away. The distances grow fast, and the physics do not care how badly we want to close them. Even if we built the most advanced rocket imaginable, something running on nuclear pulse propulsion or fusion, the fastest we could realistically push a crewed ship is a small fraction of the speed of light. A few percent, if everything goes right. At that speed, Proxima Centauri is still decades away. A more promising destination could be a century away, or two. And here is the thing nobody likes to say plainly. There is no faster option on the horizon. Warp drives are still theoretical constructs with no confirmed engineering path. Wormholes exist in the mathematics, but not in any observable form. The speed of light is not a barrier we are close to breaking. So if humanity ever wants to send people, not probes, not signals, but actual human beings to another star, the journey will almost certainly take longer than a single human life. That is not a problem you solve with better engines. It is a problem you solve by building a ship that carries not just a crew, but a civilization. One that can sustain itself, reproduce, and hold together across the generations it takes to get there. That is what a generation ship is. And it is a far stranger thing than a spacecraft. It asks human beings to live and work and raise children in a closed metal environment, surrounded by nothing on all sides, with no possibility of outside help, no rescue if something goes wrong, and no ability to turn back once a certain point has been passed. Everything the ship starts with is everything it will ever have. No deliveries, no resupply missions, no emergency services. Just the people, the machines, the biology, and the void. The idea of a generation ship is not new. Scientists and thinkers have been wrestling with this concept for nearly a century. The Russian scientist Konstantin Tsiolkovsky, who was working out the mathematics of rocketry in the early 1900s, was among the first to consider that interstellar travel might require ships designed not as vehicles for a crew, but as homes for a population. The American rocket pioneer Robert Goddard wrote about this possibility in the 1920s. And by the middle of the 20th century, writers and scientists alike had started seriously mapping out what such a ship might look like. The basic concept is straightforward to state. You build something large enough to support a stable, self-sustaining human population. You give it everything it needs to last for the duration of the voyage. You launch it toward a destination star. And then you wait. Generations pass. Babies are born. People grow old. The ship keeps going. And eventually, at the far end of a journey measured in human lifetimes, the descendants of the original crew arrive somewhere new, simple to describe, extraordinarily complicated to actually execute. Because every one of those requirements, stable population, self-sustaining systems, lasting for the voyage, contains within it a cascade of unsolved engineering, biological, social, and philosophical problems that no civilization has ever had to confront in combination. The first problem is the most obvious one: power. A generation ship needs energy for everything: propulsion, lighting, heating, cooling, air circulation, water processing, food production, electronics, medicine, manufacturing, communications. Everything that keeps a human population alive runs on energy. And on a generation ship, you cannot refuel. Whatever power system you build into the ship has to last the entire voyage. There is no service station at the halfway point. There is no option to pull over and assess. The power system is permanent from the moment of launch, and it has to work for as long as it takes to get there. Nuclear fission is the most credible option with technology that either exists or could be developed in the relatively near future. Fission reactors generate enormous amounts of energy from small quantities of fuel. A well-designed nuclear reactor burning enriched uranium or thorium could theoretically run for centuries without needing to be replaced. Modern naval nuclear reactors, the kind that power submarines and aircraft carriers, run for 20 to 25 years without refueling. A generation ship reactor would need to last far longer. But the engineering principles are sound. You would need multiple redundant reactor systems, backup power sources for critical life support functions, shielding against the radiation the reactors produce. And you would need to keep those reactors maintained by people who understand them deeply across generations. That last part is harder than it sounds. Knowledge is not automatically inherited. A reactor technician who understands the systems trains apprentices. Those apprentices become technicians and train the next group. But every time knowledge passes from one generation to the next, there is an opportunity for something to be lost or distorted. A procedure that seems obvious to a trained engineer might not be written down precisely because it seems obvious. And 3 generations later, nobody knows it. Or worse, someone thinks they know it, incorrectly, and acts on that misunderstanding. The reactor that keeps everyone alive does not accept gaps in expertise. Fusion propulsion remains theoretically superior, but practically out of reach today. Fusion reactions, the same process that powers our sun, release far more energy per unit of fuel than fission. If we ever crack controlled fusion for power generation, which has been famously described as 30 years away for the last 60 years, it would transform the economics of a generation ship entirely. The fuel for a fusion reactor could potentially be collected from the interstellar medium itself during the voyage hydrogen, which exists at low density throughout the space between stars. A ramjet-style design proposed by physicist Robert Bussard in 1960, using this principle, would, in theory, allow indefinite acceleration without carrying all your fuel from the start. The practical problems with the Bussard ramjet are serious. The magnetic field needed to collect interstellar hydrogen would have to be hundreds of miles across. The hydrogen density in interstellar space is very low, and the drag from collecting it might actually exceed the thrust the fusion produces. The concept has not been completely ruled out, but it faces substantial skepticism. Antimatter propulsion is even more energetically dense. When matter and antimatter meet, they annihilate completely and release pure energy. Nothing known to physics extracts more energy from a given mass. But producing antimatter in useful quantities requires staggering amounts of energy to begin with. It does not exist naturally in any accessible form, and storing it without it touching regular matter, which would trigger immediate annihilation, is one of the hardest engineering problems imaginable. The honest assessment for a generation ship built within the foreseeable future is that nuclear fission is what keeps the lights on. And keeping those reactors running for 200 or 500 years, maintained by people who were not alive when they were built, is one of the foundational challenges the mission planners have to solve before anything else. Everything else depends on it. Assume the power problem is solved. The next question is air. Human beings consume oxygen and exhale carbon dioxide. Do that in a sealed container long enough, and the oxygen runs out while the carbon dioxide builds up to toxic levels. On the International Space Station, this is handled by a combination of electrolysis, splitting water into hydrogen and oxygen, using electricity and chemical scrubbers that pull carbon dioxide out of the atmosphere of the station. It works well enough for a crew of 6 or 7 people on a station that stays in low Earth orbit, close enough that resupply missions arrive regularly. A generation ship does not have that luxury. Its air recycling systems have to support not 6 people, but potentially thousands, continuously, for centuries, with zero external input. The most credible approach for long-duration viability is a closed-loop biological system. Plants, algae, photosynthetic organisms that take in carbon dioxide and release oxygen, the same process that made Earth's atmosphere breathable in the first place. A sufficiently large growing area, properly managed, could theoretically maintain breathable air for a human population indefinitely, running on light and biology alone. This is not pure speculation. Biosphere 2, an experimental closed ecological system built in the Arizona desert in the early 1990s, was designed to test exactly this concept. 8 people lived inside a sealed structure for 2 years, growing their own food, recycling their air and water through biological systems, trying to function as a self-contained world. It ran into serious problems. Oxygen levels dropped unexpectedly as microbes in the soil consumed more oxygen than anticipated. Carbon dioxide levels fluctuated in ways that were difficult to control. Some plant and animal species thrived, while others crashed. The ecosystems inside did not behave the way the designers had predicted, because no model of a complex biological system captures everything. By the end of the first year, supplemental oxygen had to be pumped in from outside to keep the crews safe. Biosphere 2 is not a failure story. It is a learning story. It revealed how extraordinarily complex a closed biological system actually is. How many feedback loops and interdependencies exist that are not obvious until you seal the door and watch what happens. A generation ship would need biological life support systems, orders of magnitude more robust and well understood than Biosphere 2. Not just plants, but entire functioning ecosystems. Soil, bacteria and fungi that process nutrients and break down organic waste. Insects or other organisms that handle pollination and decomposition. Algae tanks that can rapidly adjust oxygen output as demand fluctuates with population size and activity levels. multiple redundant biological pathways so that if one species crashes, others can compensate without the whole system destabilizing. The engineering challenge here is not just building the systems. It is understanding them well enough to know what happens when something unexpected occurs. And across a voyage measured in centuries, something unexpected will occur many times. The people responsible for air quality on the ship in Generation 6 cannot phone a biologist on Earth. They need to have built-in expertise. They need diagnostic capability. They need the ability to intervene in a biological crisis using only what is available aboard. This requires a depth of ecological understanding that we currently spread across thousands of specialist researchers and institutions, concentrated into a community of a few thousand people, and maintained across generations. Water is slightly more tractable than air, but no less critical. In a sealed system, water can be recycled almost completely. Moisture from exhaled breath and sweat can be condensed and reclaimed. Urine can be processed. The International Space Station already does this, recovering more than 90% of water from urine through a multi-stage filtration and distillation process that has operated continuously for years. Wastewater from food production and hygiene can be cleaned and recirculated. In principle, a properly engineered generation ship could cycle the same water molecules indefinitely. In practice, every recycling process has losses. Materials in filtration systems degrade over time. Some water gets locked into biological waste that is not fully composted. Some is lost through processes that are difficult to prevent entirely. The ship would need reserves large enough to buffer these losses across its entire voyage. And it would need to keep its water recycling infrastructure functioning continuously and reliably. Because if the water systems fail completely, not just degrade gradually, but fail, the timeline from the start of the crisis to genuine emergency is measured in days. The redundancy requirements for water systems are extreme. Every component that could fail needs a backup. Every backup needs its own backup. And all of those systems need to remain serviceable by people who may be working with hardware that is centuries old. Spare parts are finite. Manufacturing capability aboard the ship extends the life of components, but it also requires raw materials and the expertise to use them. A generation ship probably needs to carry extensive raw material stocks alongside its mechanical systems. Not just spare parts, but the materials to make new spare parts when the spares run out, and the people who know how to make them. Food is the most intimate and culturally loaded of the basic survival requirements. And on a generation ship, it has to be produced entirely on board. No deliveries, no imports, no hunting or gathering from an outside environment. Every calorie consumed by every person aboard has to come from something grown, cultivated, or synthesized within the ship's hull. Agricultural systems for a generation ship would likely center on high-yield, space-efficient crops. Wheat, rice, potatoes, soybeans, sweet potatoes, leafy greens. These are the crops that provide the most nutrition per square foot of growing area. Hydroponic and aeroponic systems, where plants grow in water or mist rather than soil, are more efficient than traditional agriculture in terms of space and water use. LED grow lights, tuned to the wavelengths plants actually use for photosynthesis, can make indoor farming energy efficient enough to be viable in a power-constrained environment. The International Space Station has grown lettuce and radishes using exactly these techniques, and the results have been promising. But feeding a crew of 6 with a small hydroponic garden is a very different engineering problem from feeding a population of several thousand across multiple centuries. Soil-based agriculture would likely also be necessary. Real soil, with its community of microorganisms, provides a resilience and complexity that hydroponic systems can struggle to match for all crop types. It also plays a role in the broader biological air and water recycling systems, processing nutrients and supporting the microbial communities that the whole biological life support depends on. A generation ship would probably need substantial agricultural decks. Not just efficient factory farming operations, but something closer to actual working ecosystems that could be managed, adapted, and maintained by people who understood farming as a living practice, not just a technical procedure to follow from a manual. Animals are a more complicated question. Livestock require significant space, water, and feed relative to the nutrition they provide. They produce waste that has to be managed. They have their own health challenges and require veterinary care. But they provide not just protein, but fats, vitamins, and micronutrients that are difficult to get from plants alone in the right combinations. More practically, they provide nutritional redundancy. If the grain harvest fails, one cycle, having animals to draw on could be the difference between a serious crisis and a catastrophic one. Smaller animals, chickens, rabbits, insects, are far more resource efficient than cattle or pigs. Insects, in particular, can convert organic waste into protein with remarkable efficiency. They require minimal space, breed rapidly, and can fill an important nutritional role without placing enormous demands on the ship's food system. Fish and shellfish in enclosed aquaculture systems could provide another nutritional layer. Tilapia, carp, and similar hardy species have been grown in closed systems on Earth. They can convert algae and plant waste into protein and can be integrated into the broader biological recycling systems rather than operating as a separate resource drain. No single food source would be enough on its own. The ship's nutritional system would have to be a web of interlocking production chains, each one backing up and feeding into the others. Failure in one area needs to be absorbable by the others without triggering a cascade failure. And the people managing those systems need to understand not just their own piece, but how it connects to everything else. Medicine deserves its own consideration, because it is an area where the gap between what is needed and what is easy to provide grows significantly over time. A generation ship at launch would carry doctors, surgeons, specialists across multiple medical fields. It would carry pharmaceutical supplies, surgical equipment, diagnostic tools. But pharmaceutical supplies have shelf lives. Surgical equipment wears out and needs maintenance. Diagnostic tools require calibration and eventually replacement. And the medical knowledge on the ship has to cover, for centuries, everything that a planetary civilization, with hospitals and specialist centers and pharmaceutical supply chains, normally handles. On Earth, if someone develops a rare cancer or needs a complex organ transplant, they go to a major medical center. They are treated by specialists who have spent decades developing expertise in that specific area. A generation ship cannot maintain that level of specialization. Its population is too small. The training time required to produce a neurosurgeon or a cardiac specialist is too long to have redundant coverage in every specialty. The ship's medical community will be capable of a wide range of care, but it will have gaps. And those gaps will encounter patients who need exactly what is missing. Pharmaceutical production capability is one partial answer. A ship equipped with the ability to synthesize medicines from basic chemical feedstocks can maintain a supply of critical drugs indefinitely, as long as it has the raw ingredients and the expertise to use them. Biotechnology, particularly the ability to produce biological medicines like antibiotics, vaccines, and hormone therapies, adds another layer. Gene therapy and targeted treatments could potentially address conditions that would otherwise be untreatable in a resource-constrained environment. The medical systems on a generation ship would have to be more self-sufficient than any medical facility that currently exists. And they would have to maintain that self-sufficiency across generations of medical professionals who trained and practiced entirely aboard the ship. The biological systems are complicated, but they are at least physical systems that engineers can study, test, model, and refine. The harder problem, the one that most generation ship proposals struggle to address adequately, is the human one. Specifically, what happens to people when they spend their entire lives in a sealed metal world, surrounded by the same few thousand people, going nowhere that anyone aboard will ever see? Humans did not evolve for this environment. We evolved on open savannas and in forests, in landscapes that changed with seasons and weather, in social groups embedded within a broader natural world. Our brains are tuned to horizons, to weather, to the sensory richness of a living planet that varies endlessly. A generation ship offers none of that. The sky is metal. The horizon is a curved wall. There is no weather, no seasons in any natural sense, no outside. The view from any window, if there are windows at all, is the same darkness with the same stars for years and decades on end. The same stars, growing very slightly different in apparent position as the centuries pass, but not in any way that a human being would notice on any given day. The psychological literature on extreme isolation and confinement is sobering. Researchers studying Antarctic winter-over crews, the small groups of scientists who spend months in total darkness and isolation at research stations at or near the South Pole, consistently document what they call the winter-over syndrome: cognitive slowing, emotional blunting, irritability and interpersonal friction, a kind of diffuse low-grade depression that settles over the group as the months of isolation accumulate. Memory and concentration deficits that are measurable on testing. These are effects that show up in people who know they are going home. They know the supply plane is coming in the spring. They know the isolation ends. A generation ship removes that certainty entirely. The people aboard know that the ship is their entire world. Not temporarily, permanently. They will never walk on soil under an open sky. They will never experience rain or snow. They will never go somewhere their neighbors have not also been. The closed, high-density, high-stakes social environment of a generation ship creates a very specific kind of interpersonal pressure that has no good analog in current human experience. The closest comparisons are submarines, Antarctic stations, and isolated research outposts. All of these are studied carefully by psychologists interested in long-duration space missions. All of them show characteristic patterns of stress, conflict, and psychological strain that emerge reliably after extended confinement. And all of them end. The submarine surfaces. The Antarctic crew rotates home. For a generation ship, there is no surfacing, no rotation home, no end to the confinement except the destination, which most of the people who ever live aboard will never see. The social dynamics in an environment like this are hard to predict with confidence. Small communities under stress can become tight and resilient people depending on each other, valuing each relationship deeply, building the kind of bonds that only develop under shared hardship. Or they can fracture. Factions, forming around real or perceived differences. Grievances accumulating without resolution. Trust eroding slowly until the social fabric is more fragile than anyone admits. Conflicts that on Earth would be resolved by one party, walking away, moving to a different city, a different country, a different life, have nowhere to go on a ship. You cannot leave. You cannot escape. The person you had a serious conflict with yesterday is sitting at the next table at dinner tonight. And every night after that. For decades. The ship's governance would have to include effective conflict resolution mechanisms. Not just rules, but processes. Not just penalties, but genuine ways for people to feel heard, to have genuine grievances addressed, to have paths toward resolution that do not require either submission or permanent enmity. Without that, conflicts in a closed population accumulate. They do not dissipate naturally the way they can in an open society where people can create distance. They stay in the room with everyone forever. The governance question is one that gets surprisingly little attention in technical discussions of generation ships. But it may ultimately matter more than the reactor design. The people who board the ship agree to the mission. They understand what they are committing to. They voted for the captain, or accepted the command structure, or signed the founding charter. But their children did not. Their grandchildren did not. And the people who actually arrive at the destination, 300 years after departure, are living under a governance structure they had absolutely no part in creating. They are subject to rules and obligations written by ancestors they may view as having no particular authority over their lives. The Mayflower Compact, signed aboard the Mayflower in 1620, was an attempt to address exactly this kind of problem. A small group of people cutting loose from established authority on a long voyage to an unknown destination, trying to create a framework for governing themselves in a situation nobody had fully planned for. It was a single page. It worked, more or less, for a single crossing of the Atlantic. A generation ship would need something far more sophisticated. Something that could adapt as circumstances changed across centuries. Something that granted the people actually alive, not the founders, not the mission planners back on Earth, who are long gone genuine authority over their own lives and their own community, but also something that protected the mission itself. Because if the third generation decides by majority vote to change course, to slow down, to stop the ship and turn it into a permanent habitat station rather than continuing to the destination the mission ends, the tension between the rights of the living population and the obligations inherited from the founding generation is not a problem any existing political philosophy has cleanly resolved. It is related to deep questions about intergenerational justice and consent that political philosophers have debated for centuries without reaching consensus. On a generation ship, it is a problem that cannot be deferred. It has to be built into the structure of the society from the start, with enough flexibility to accommodate the changes that centuries of living will inevitably bring. Some researchers propose a layered constitutional structure, a core of inviolable principles, those that protect the mission's fundamental requirements and the basic rights of everyone aboard that cannot be changed by any vote, and a larger body of law and governance that can be revised by the living population through legitimate democratic processes. The challenge is deciding which principles are inviolable and which are not, and ensuring that the inviolable category does not become a mechanism by which the founding generation's preferences permanently override the living generation's autonomy. There is no perfect solution, but the generation ship that never thinks carefully about this has already planted the seeds of a governance crisis that could emerge at any point in the voyage when the living population decides, for any reason, that the obligations they inherited are not ones they are willing to accept. The genetic question is more biological than political, but it has equally serious implications for how long the ship's population can remain viable. Genetic diversity is the deep reserve of resilience in any population. When a disease appears, or an environmental stress, or a shift in conditions, the members of the population vary in their responses. Some are more resistant. Some cope better. That variation is what allows the population to survive and adapt. Reduce the genetic diversity, and you reduce the population's ability to respond to challenges it has not yet faced. Push it low enough, and you start seeing the accumulation of harmful recessive traits. Inbreeding depression, reduced fertility, increased rates of developmental problems, compromised immune function. The eventual decline of the population's reproductive viability if nothing is done to address it. This is not a theoretical concern. It has been documented in isolated human populations on Earth, in island communities, and in geographic isolates where limited gene flow over generations produced measurable genetic effects. The minimum viable population size for a long-duration space voyage has been studied carefully by population geneticists. Published estimates vary depending on assumptions, but a widely cited analysis suggested that a minimum founding population of around 40,000 individuals would be needed for a voyage of several hundred years, accounting for potential catastrophic events, population fluctuations, and maintaining sufficient diversity to keep the population at the destination genetically healthy. That number might seem large, but it is actually conservative. It assumes no catastrophic losses, reducing the population to a fraction of its founding size. It assumes reasonably thoughtful management of reproductive patterns to ensure no family lines dominate the genetic pool. It assumes a voyage duration that many interstellar destinations would far exceed. Smaller founding populations are possible if reproduction is carefully managed, ensuring that no particular lineage is overrepresented, that pairings are distributed to maximize genetic diversity, that the population avoids genetic bottlenecks from small cohort sizes in any generation. But this requires a kind of social engineering around reproduction that would be deeply uncomfortable for people who hold reproductive autonomy as a fundamental value. You are essentially asking people to consider the genetic health of the entire population as a factor in who they have children with, and potentially in how many children they have. Some proposed solutions involve frozen genetic material, a vast library of sperm, egg cells, or embryos from donors on Earth, covering enormous genetic diversity, far more than any reasonably sized crew could carry in their living bodies. These could be used to introduce fresh genetic material at intervals throughout the voyage, supplementing the natural reproduction of the crew and preventing the genetic narrowing that isolation inevitably creates in small populations. The technology to do this exists, at least in basic form. Cryopreservation of human reproductive cells is routine medicine today. Maintaining frozen samples viable for centuries requires solving problems that current technology has not yet fully addressed. But the principle is sound, and the technical challenges, while significant, are not obviously insurmountable. A generation ship, equipped with a sufficiently large genetic library and the knowledge and equipment to use it, could maintain much higher effective population diversity than its actual living headcount would suggest. The ship itself, the physical vessel, faces threats from outside that no mission planner can fully anticipate or entirely prevent. Cosmic radiation is a constant presence in deep space. Earth's magnetic field and atmosphere protect us from most of the radiation that streams through the solar system. A generation ship in interstellar space has neither galactic cosmic rays, high-energy particles accelerated by supernova remnants and other violent processes across the galaxy penetrate almost any practical amount of shielding. They are not stopped by a few inches of metal. They pass through the ship and through the people inside it, depositing ionizing energy in tissue. Solar energetic particles, emitted by stellar flares, are also dangerous during the early part of any journey near a star. Long-term exposure to this radiation increases cancer rates. It damages DNA in ways that accumulate over time. It can affect the central nervous system, altering cognition and mood in ways that compound the already significant psychological challenges of deep space confinement. For a voyage measured in centuries, radiation exposure is not merely a risk factor to be minimized. It is a certainty that has to be designed around. The most effective practical shielding against cosmic radiation is mass. Dense material between the occupants and the outside. Water is an excellent radiation shield for certain particle types. Storing the ship's water supply in tanks surrounding the habitation areas serves a double purpose: life support resource and radiation protection at the same time. Lead and polyethylene are also effective, but any shielding adds mass. And mass, for a spacecraft, means more energy required to accelerate to operational speed and to decelerate at the destination. The design of the shielding architecture requires balancing the radiation exposure budget against the mass and structural consequences of the shielding chosen. There is no perfect answer. The ship's crew will receive more radiation over their lifetimes than people on Earth. The question is, how much more? And whether that excess can be reduced to a level that allows a healthy population across centuries. Micrometeorites and interstellar dust are another perpetual threat. Space is not empty. It contains dust grains, small particles of rock and ice, traveling at whatever their relative velocity to the ship happens to be. A particle the size of a grain of sand, striking a hull at several miles per second, carries significant kinetic energy. Over centuries of travel through the interstellar medium, a generation ship's outer hull will be struck by these particles constantly. Most impacts are negligible, but the statistical tail of impact events includes those large enough to breach the outer hull layers. Multi-layered hull designs a series of thin outer shields that fragment and spread incoming particles before they can deliver their full energy to the structural hull, are the standard engineering response. The Whipple shield, developed in the 1940s by astronomer Fred Whipple, uses exactly this principle. A thin outer bumper sheet, spaced away from the main hull, causes incoming particles to vaporize and disperse before they reach the interior. Modern spacecraft use refined versions of this design. A generation ship's hull would incorporate advanced versions across every external surface. But over centuries, the outer hull layers accumulate damage. The bumper shields erode. The hull itself develops microstructural fatigue. All of this needs to be inspectable and repairable by people whose relationship to the original engineering is purely historical. Any serious hull breach, one that threatens the pressure integrity of inhabited spaces, requires rapid response by people with the right materials, the right tools, and the right knowledge. The people alive at the moment of such a breach may be 12 generations removed from the engineers who designed the hull. They need to understand it well enough to fix it under pressure with whatever is available. This returns us to the problem of knowledge, which is arguably the deepest and most underappreciated challenge facing any long-duration generation ship. A modern spacecraft is built by thousands of engineers across hundreds of disciplines. The knowledge required to design, build, and operate that ship is distributed across an entire industrial civilization. When something goes wrong, you call the manufacturer. You connect to a team of specialists. You have access to the full library of human technical knowledge through communications with Earth and through the global network of expertise. A generation ship in interstellar space has none of that. Signals from Earth take years to arrive and carry no real-time problem-solving capability. The knowledge base that keeps the ship alive has to be entirely contained within the ship, not just in computer systems, but in the minds and practiced hands of the people aboard. Because computer systems can fail. Data can be corrupted through radiation damage or hardware degradation. Storage media that is perfectly reliable for decades may not be perfectly reliable for centuries. And reading a manual about how to repair a complex system is not the same as actually knowing how to do it. There is a difference between having information and having knowledge. Information is data stored on a medium. Knowledge is understanding that lives in a trained human mind that can be applied flexibly to novel situations, that can improvise when the textbook scenario does not quite match what is actually happening. A generation ship needs that kind of knowledge, deep, practical, flexible, across the full range of systems that keep it alive: reactor systems and nuclear physics, biological life support and ecosystem dynamics, water and waste, recycling, chemistry, and engineering, agricultural science, from soil microbiology to crop genetics, medical science, from surgery to pharmacology to pathology, materials, science, and fabrication, navigation and orbital mechanics, computer systems and software, hull, engineering, and structural maintenance. And it needs the next generation to understand all of it equally well, and the generation after that. For centuries. There is a concept in anthropology called cultural transmission fidelity, how accurately knowledge and practices pass from one generation to the next. On Earth, we have universities, trade schools, apprenticeship systems, professional cultures, libraries, peer review, and the ability to consult with experts anywhere in the world. These institutions evolved over thousands of years, specifically because accurate transmission of complex knowledge is not automatic. It requires deliberate, ongoing, institutional investment to maintain. A generation ship would need to build something equivalent for a society of a few thousand people, covering the full range of technical knowledge needed to keep the ship alive. A rigorous curriculum covering every critical system. A culture of mentorship and apprenticeship embedded deeply enough to survive generational changes. An ethic that treats technical competence as a survival imperative, not just a career path. And that culture would have to hold across the centuries with the same reliability as the reactor containment vessels. because the failure mode of knowledge loss does not announce itself with an alarm. It happens quietly, over generations, until the day someone opens a panel on a system they are supposed to understand and realizes, with growing dread, that they do not actually know what they are looking at. There is a phenomenon that sociologists and generationship theorists call mission drift. The founding generation knows why they are on the ship. They lived on Earth. They made a decision to leave. They carry the weight and the meaning of that decision in everything they do. The destination is real to them because Earth was real to them. They remember what they left behind, and they believe in what they are going toward. The second generation grows up on the ship. They have no memory of Earth. Their parents tell them about it. They learn about it in school. But it is an abstraction. A story told by people who grew up somewhere else. The third and fourth generations are even further removed. Earth is ancient history. As distant and possibly as mythologized as the Roman Empire is to us now, the destination is a vague promise that their great-grandparents made on behalf of everyone who would come after. And the mission, the obligation to maintain the ship, to follow the course, to arrive at the destination, is something they inherited rather than chose. Maintaining commitment to a long-term goal across generations is one of the hardest things any institution has ever attempted. Religions have done it, more or less, over centuries and millennia. Cultural traditions have been preserved across time, but religions and traditions offer meaning that connects to something felt as larger than any individual life. They give people a reason to carry the tradition that is not just obligation, but genuine belief. A generation ship needs a belief system, a shared meaning framework that makes the mission feel worthy of the sacrifices it demands. Not propaganda enforcing compliance. Not institutional coercion. Something that people can genuinely hold on to and genuinely transmit to their children as something worth holding. Something that makes the meaning of the voyage feel real, even to the person born in year 150 of the flight, who has never seen a star from a planetary surface and never will. This is a problem of culture as much as governance, of story and ritual and shared practice, of making the mission feel, across the generations that will never see its completion, like something worth being part of anyway. One partial technical answer to some of the human problems is the idea of suspended animation or hibernation. If you could put people into a physiological state of reduced metabolic activity, dramatically slowed heart rate, lowered body temperature, suspended consciousness, you could potentially carry a crew through a centuries-long voyage without all of them experiencing it in real time. Wake a rotating watch crew for maintenance and monitoring periods. Keep the rest in deep physiological rest, not experiencing the passage of time, not accumulating the psychological damage of prolonged confinement, not aging at normal rate, and arrive at the destination without the full generational burden of living a complete civilization aboard a ship for centuries. This is appealing as a concept. The biological reality is considerably more complicated. True suspended animation in humans does not currently exist. Medical hypothermia, lowering body temperature to protect patients during surgery or cardiac events, does exist, and patients can survive cooled to around 28 degrees Celsius, that is 82 degrees Fahrenheit, for periods of hours. Research programs have been exploring whether this can be extended to days, with some promising early results in animal studies. But weeks, months, years, or centuries of metabolic suspension, with full revival of cognitive function and biological health, has not been demonstrated. The fundamental challenge is that cells do not just slow down cleanly when cooled. Ice crystal formation at low temperatures damages cell membranes in ways that can be lethal. Chemical processes that keep cells alive do not all slow proportionally with temperature, creating imbalances that can accumulate into serious damage. Vitrification, replacing the water in tissues with glass-forming compounds that prevent ice crystal formation, is a technique used to preserve certain types of cells and embryos. But vitrifying an entire living human being and then reviving them is an entirely different scale of challenge. Every organ system in the body has different requirements and different tolerances. The brain, in particular, is extraordinarily sensitive to the kinds of cellular disruption that cryogenic processes produce, and is the last organ you want to have functioning suboptimally when people wake up needing to run a ship. Research continues, and there are serious scientists working on long-duration human torpor. Some clinical work has explored deep hypothermia in carefully managed medical contexts. Progress is real, if measured. But for a generation ship designed and launched anywhere within the foreseeable future, suspended animation cannot be assumed to be a reliable option. The design would have to account for people living full lives aboard the ship, with all of the generational, psychological, genetic, and social challenges that reality entails. Some proposals bypass the population biology problems entirely by changing what the ship carries. Seed ships, not living humans, but frozen embryos, or cryopreserved reproductive cells, or even just the DNA sequences needed to reconstitute human biology. The raw genetic material required to seed a population at the destination, rather than carry one the whole way. A seed ship would be dramatically smaller than a full-generation ship. Less mass, less power, less life support complexity. It could be built more quickly and potentially travel faster. And at the destination, an automated system would revive the embryos, raise the resulting children in some kind of artificial care environment, and gradually bootstrap a human presence on the new world. The ethical complexities here are significant. You are bringing human beings into existence with no parents, no living community, no culture, in a completely alien environment, dependent entirely on automated systems for their survival and development. The children who emerge at the other end face challenges of identity and psychological formation that are genuinely hard to think through. They would know they were created by a machine from material that crossed the void. They would have no living elders, no grandparents, no oral tradition, no one to tell them what things mean or how the world works in terms beyond what a system was programmed to say. They would be human in biology, but in some sense unprecedented in their formative circumstances. The engineering complexity is also enormous. The artificial care and education systems would have to function flawlessly across centuries, adapt to circumstances their designers could not fully anticipate, and produce healthy, functional adults from infants with no adult role models other than whatever the automated systems provided. There is also a version of this concept where some embryos are kept frozen aboard a crewed generation ship as a genetic reserve, not the primary population, but a backup population. A library of potential people who could be brought into existence if catastrophic population loss threatened the mission. This is less ethically complicated because it supplements, rather than replaces, a living human community. But it raises its own questions about how decisions would be made. Who decides when to activate the reserve? By what criteria? Applying what principles? With what authority over the resulting lives of those who emerge? These are not unanswerable questions. But they require answers before the ship launches, built into whatever governance structure it carries. The question of what happens at the other end deserves as much serious thought as what happens in the middle. A generation ship approaching a destination star after 200 or 300 years of travel is not arriving at a verified, habitable world. We can study the destination system from here using telescopes and spectroscopy. We can determine whether a planet has the right mass and orbital distance from its star. We can analyze its atmospheric chemistry for signs of water vapor, oxygen, carbon dioxide. We can look for biosignatures, chemical signals that might indicate biological activity. The James Webb Space Telescope has already begun demonstrating what is possible in this area, analyzing exoplanet atmospheres from our current position in the solar system with a precision that would have seemed extraordinary just a decade ago. But we cannot know with certainty, from trillions of miles away, whether a world is actually livable, whether its surface gravity is comfortable for humans, whether its day length is compatible with human biology, whether its native microbiology would be benign or dangerous, whether its mineral chemistry would support agriculture, whether its weather patterns include anything so severe as to be immediately threatening. The ship arrives. The people look at this new world, this colored disk hanging in a sky that is not Earth's sky, orbiting a star that is subtly different from the one their ancestors left behind. And they have to make a decision. Is it safe to send people down? Can we survive here? Should we go? This decision is made by people who have spent their entire lives in deep space, who have never stood on solid ground, with wind on their faces and open sky above them, who only know what planetary surfaces are like from recordings made centuries ago on a world none of them have ever seen. The planet below them might be beautiful, might have an atmosphere that is almost right, might have liquid water and something green in what might be photosynthesis, or it might be subtly hostile in ways that will only become apparent after people have committed to being there. The decision to descend, to make that commitment, to leave the ship that has been the entire world of their civilization for 3 centuries. That is one of the most consequential decisions any group of human beings has ever made. And they will make it with information that is never quite complete. They will make it knowing that the ship cannot easily take them back. They will make it knowing that whatever they choose, their descendants will live with the consequences. There is a version of the generation ship story that goes well. The ship launches with a well-designed population, sufficient genetic diversity, robust and redundant life support, a thoughtful governance structure, and a culture that manages, somehow, to preserve both technical knowledge and a sense of shared purpose across the centuries. Generations come and go. The ship holds together. Conflicts arise and are resolved by processes that the community trusts. Systems fail and are repaired by people who were trained well and who trained their successors equally well. Knowledge passes from the old to the young without critical losses. The agricultural systems produce enough. The reactors keep running. The air stays breathable and the water clean. The genetic diversity stays sufficient. And the people aboard, not the same people, never the same people, but a continuous human community maintain enough coherence to keep moving forward with purpose. The stars move imperceptibly in the forward cameras across the decades and the centuries. And then, In the lifetime of the 7th or 9th or 12th generation, one star grows brighter than the others. Perceptibly brighter, year by year. The crew adjusts course. The long deceleration burn begins, trading velocity for time, trading speed for the ability to stop rather than fly past. A planetary system resolves itself from a point of light into a collection of distinct worlds. And among them, not too close to the star, not too far, there is a planet with blue and white and brown, and perhaps a faint suggestion of green in its coloring. Not Earth, but something. The people who stand at those cameras and look at that planet are the products of centuries of isolation, adaptation, and survival. They are human beings, genuinely and fully, but shaped by a world their ancestors would find unrecognizable. They are ready, or as ready as anyone can be, for what comes next. That is the version of the story that works. The version that does not work has many possible shapes. Some are sudden. A catastrophic reactor failure that cannot be contained before it becomes dangerous. A hull breach in a critical section that the people alive at that moment do not have the knowledge or materials to repair. A rapidly spreading disease in a population that has been isolated long enough to have lost the broad immune exposure that living populations on Earth maintain through constant microbial contact. These are the dramatic failure modes. They make for compelling stories. But the more realistic failure modes are slower, subtler. A gradual loss of technical knowledge over generations until critical systems are operated by people who understand the procedures but not the principles, who can follow the checklist but cannot diagnose the problem when the checklist does not cover what is happening. A cultural drift away from the mission's founding purpose until the ship's society no longer agrees or no longer cares whether arriving at the destination is something they want. A genetic bottleneck from a period of population stress, a severe disease outbreak, a period of extremely low fertility, an accident that kills a disproportionate share of one genetic line that reduces diversity enough that its effects accumulate quietly across the following generations. A governance breakdown that produces a factional conflict. The society lacks the institutional tools to resolve before it becomes something that tears the community apart. These slow failures are harder to see coming and harder to correct once they are underway. They do not trigger alarms. They accumulate across decades, visible only in retrospect as a trajectory that has been bending the wrong way for a long time. The hardest thing about preventing them is that they require the living generation to take seriously the implications of trends that have not yet become crises. To act on the basis of projections rather than emergencies. That kind of institutional foresight is rare in human societies. Building it into a generation-ship society and keeping it alive across centuries is perhaps the most ambitious social engineering challenge the whole enterprise entails. There have been serious attempts to think through how a generation-ship society might be structured to avoid these failure modes. Some researchers propose what they call a city-state model. The ship is divided into semi-autonomous communities that have significant local governance but share critical infrastructure and operate within a common framework. This prevents power concentrating in a single authority that could become tyrannical, incompetent, or simply detached from the reality of life in different parts of the ship. It creates diversity of social experiment. Different communities might develop different approaches to education, work, cultural expression, and communal life. The approaches that work better can be observed and adapted by others. It also creates redundancy. If one community experiences serious social problems, the others do not necessarily have to go down with it. Others have proposed deliberate cultural design. Not the engineering of compliance, but the careful construction of rituals, stories, institutions, and symbols that reinforce the ship's purpose and community cohesion across the generations. The way that militaries build unit cohesion through shared ceremonies and rituals. The way that long-lived religious and cultural traditions preserve identity across centuries through practices that connect each living generation to the ones before. Applied deliberately to a generation ship by people who understand that culture is not automatic, but is always the result of choices about what to transmit and how. The crew would need art, music, literature, sport, play, celebration, and the space for genuine human creativity, not as luxuries to be tolerated if resources allow, as necessities. The things that make human life feel worth living are not separate from the survival mission. They are part of it. A society that loses its cultural vitality, that becomes purely transactional and functional, loses something essential long before any physical system fails. It loses the psychological resilience to handle the hard years. The motivation to pass along not just technical skills, but meaning. The belief that arriving somewhere and building something is worth whatever cost the journey demands. The scale of the ship itself matters enormously and creates one of the central tensions in generation ship design. Larger populations are more genetically and socially robust. More people means more genetic diversity and more resilience against the population crashes and bottlenecks that small isolated communities are vulnerable to. More people also means more specialists, more redundancy in critical knowledge, more social diversity. But larger ships are harder to build, harder to power, and harder to accelerate to the velocities needed to make an interstellar journey possible within any time frame that preserves the mission's purpose. The 40,000 figure from the population genetics literature would require a ship of staggering size. Imagine a structure designed to carry 40,000 people, their agricultural systems, their water and air recycling infrastructure, their reactor systems, their medical facilities, their workshops and schools and cultural spaces, and everything else a functioning civilization requires. The mass would be immense, probably measured in millions of metric tons. Accelerating that mass to even a fraction of a percent of the speed of light requires energy that dwarfs anything in the current human capability. One proposed architecture addresses this by not using a single ship at all, but a fleet. Multiple vessels traveling together, close enough to communicate and assist each other regularly, far enough apart that a single catastrophic failure does not destroy the entire mission in one event. Crew can transfer between ships when needed. Genetic material can be shared to prevent individual ship populations from bottlenecking independently. Resources can be redistributed if one ship's production systems outperform another's. If one ship suffers a systems failure, others can provide emergency support. This dramatically improves the overall mission's resilience. The loss of one ship becomes a terrible tragedy, not a mission-ending catastrophe. It also dramatically increases the cost and complexity of the initial launch. But, from a survival standpoint, a fleet of 10 or 20 moderately sized ships is far more robust than a single vessel carrying all the same people and all the same single points of failure. Before we go any further into the human side of this, it is worth understanding the physics of the voyage itself more concretely. because the constraints that physics imposes shape every other decision. The distance to even the nearest stars is measured in light years. A light year is the distance light travels in 1 year, moving at roughly 186,000 miles per second. Proxima Centauri, our nearest stellar neighbor, is 4.24 light-years away. The next interesting system, beyond that Alpha Centauri A and B, a pair of sun-like stars that orbit each other, sits at the same distance, as they are part of the same triple star system. Tau Ceti, a sun-like star with a confirmed planetary system that has drawn significant scientific interest, is about 11.9 light-years away. These distances translate into travel times that depend entirely on how fast the ship can go. At the speed of the fastest probes ever, to leave the solar system around 38,000 miles per hour, the numbers are completely impractical. 70,000 years to Proxima Centauri. More than 200,000 years to Tau Ceti. Generations are not the right unit of time at these speeds. Dynasties are not the right unit. Species-level evolutionary timescales are closer. So, any realistic generation ship scenario requires propulsion vastly beyond what we have today. A nuclear pulse propulsion system of the kind studied under Project Orion in the 1950s and 60s, which worked by detonating nuclear warheads behind a large pusher plate, could, theoretically, reach a few percent of the speed of light. At 1% of light speed, Proxima Centauri is about 430 years away. At 5% of light speed, it is about 85 years. At 10%, roughly 40 to 45 years. These are the timescales we are actually talking about for a serious interstellar mission using nuclear propulsion. Decades to centuries, depending on the destination and the propulsion capability. Most serious proposals land somewhere between a 50-year minimum and a few hundred years for destinations beyond the nearest star systems. That is the window within which a generation ship has to function. Not thousands of years. Not tens of thousands. But still long enough that the people who launch the ship will not be the ones to arrive. The deceleration problem is as significant as the acceleration problem. A ship traveling at a meaningful fraction of light speed has enormous kinetic energy. Stopping takes as much effort as getting up to speed. And unlike acceleration, which can in principle be done over time with a steady thrust, deceleration at the destination requires a way to shed that energy. Options include the reverse burn, using the same propulsion system in reverse, which requires having reserved enough fuel for a full deceleration burn that mirrors the acceleration burn, or magnetic sail braking, which uses a large superconducting loop to interact with the interstellar medium and bleed off speed over time, or in-system braking, using the gravity of the destination star or its planets to help slow the ship through a series of gravitational capture maneuvers. Each approach has trade-offs. The reverse burn option roughly doubles the fuel requirement for the whole mission. Magnetic sail braking works gradually and requires maintaining large, delicate structures for extended periods. Gravitational braking only works once the ship is already in the destination system and requires precise navigation through an environment whose exact configuration will not be fully known until the ship arrives. All of these have to be planned from the start. The ship that launches without a credible deceleration strategy is committing its passengers to a flyby of the destination system passing through at high speed, unable to stop, continuing on into the void beyond. That is not a mission. That is an elaborate way to travel a very long way and accomplish nothing. The propulsion system and the life support systems are the two most critical engineering domains. But there is a third that ties everything together, and it is one that receives less attention than it deserves: navigation. In interstellar space, there are no GPS satellites. There are no ground stations. There is no constant communication with mission control, providing course corrections. The ship navigates by stars, measuring the apparent positions of known stars and calculating its position and velocity relative to them. This technique, called stellar navigation or celestial mechanics, has a very long pedigree on Earth. Sailors navigated by the stars for millennia before modern technology, but stellar navigation is different in important ways. As the ship moves, the apparent positions of stars change due to parallax, the shift in apparent position produced by the changing viewing angle. The faster the ship moves and the further it travels, the more significant these parallax shifts become. The star field the ship sees from deep interstellar space looks meaningfully different from the star field visible from Earth. The navigation systems have to account for this. They have to measure stellar positions with extraordinary precision, compute the ship's actual position from those measurements, compare that to the intended course, and calculate any corrections needed. All of this requires functioning instruments and the knowledge to use them correctly across the centuries of the voyage. A navigational error that produces a small course deviation early in the voyage can result in the ship arriving at completely the wrong place or missing the target system entirely, if it is not caught and corrected. The destination is a tiny target in an enormous void. A few degrees of error sustained across decades means missing it by an enormous margin. The people responsible for navigation in Generation 150 cannot afford to be less competent at this than the people in Generation 1. The instruments have to be maintained to the same precision. The methods have to be understood at the same depth. The culture of rigor around navigation has to be as robust in the final decades of the approach as it was at the start of the voyage. There is another dimension of the navigation challenge that is easy to overlook. The destination star, when the mission is being planned, is known with good precision in terms of its position and its properties. We can observe it from Earth with powerful telescopes. We can measure its spectrum, its luminosity, its mass. We can identify planets in its system using transit photometry, radial velocity measurements, and direct imaging. We can characterize those planets' sizes, orbital periods, and in some cases atmospheric compositions. But we cannot see the destination system as it will be when the ship arrives. If the voyage takes 250 years, the observations we made at the time of launch are 250 years old by the time the ship arrives. Stars change. They flare. Their activity levels vary across decades and centuries. Planets have seasons and weather and geological processes. A planet that looked promising from Earth might, on arrival, turn out to be in a different phase of its climate cycle, might be showing more cloud cover than the early observations suggested, might have had a significant volcanic event that altered its atmospheric chemistry. None of this can be known in advance. The ship has to carry instruments capable of performing its own characterization of the destination system as it approaches. Has to have the expertise to use those instruments properly, and has to be able to make decisions based on what it finds without waiting for confirmation from Earth, because Earth's response to any communication will arrive years later. This is one of the reasons that full autonomy, genuine decision-making capability within the ship's community is not optional. It is required by the physics of communication delay. The ship cannot defer difficult decisions to mission controllers who are decades away. The people on the ship have to be able to assess the situation themselves and act. The communication question deserves its own careful treatment. For the early part of the voyage, while the ship is still within the solar system, or just beyond it, communication with Earth is possible with reasonable delay. When Voyager 1 crossed the boundary of the solar system, its radio signals took about 17 hours to reach Earth. A ship at the edge of the solar system might be a few light hours away. Still in contact, still able to exchange messages within a day. But as the ship moves outward into interstellar space, the communication delay grows. At 1 light year out, messages take a year each way. At 2 light years, 2 years each way. By the time the ship is halfway to its destination, messages from Earth are already several years old. By the time they arrive, any response will be equally delayed in return. The practical consequence of this is that communication with Earth ceases to be meaningful for real-time decisions very early in the voyage. The people aboard cannot ask for help with a medical crisis and receive useful guidance. They cannot report a system's failure and receive engineering assistance in time. They cannot ask a question and expect an answer within any time frame that matters for the situation they face. What communication with Earth can provide is cultural continuity, news of developments on Earth, new scientific knowledge, art, literature, music, human voices from the world the mission came from. These things have real, psychological value. They connect the ship to something beyond its own hull. They remind the people aboard that they are part of something larger. But the signal weakens as the distance grows. Transmitting from interstellar distances requires enormous power and highly directional antennas. Receiving from Earth requires equipment that can detect signals that have spread across the expanding sphere of the transmission's range. At some point in the voyage, the signal from Earth becomes too faint to receive reliably. Without equipment of a scale, the ship may not be able to maintain. At some point, the connection to Earth effectively ends. Not suddenly, not on a specific date, but gradually, over years, the voices from home grow quieter. The news arrives later and later. The cultural threads thin. And eventually, the ship's community becomes, for all practical purposes, an independent civilization. The only civilization it has. This transition from connected mission to isolated community is one of the psychologically most significant events in the voyage. It probably needs to be anticipated, planned for, and marked in some way that the community can process. Because it is genuinely a loss. And losses that are not acknowledged tend to find their way out in other forms. The question of what happens to children born on the ship is central to everything. Children are not a side effect of the generation ship concept. They are the mechanism by which the mission continues. They are the reason the ship can function across more than one generation at all. But they are also people who did not choose any of this, who arrive in a world entirely unlike anything their biology was shaped for, who grow up with a sky that does not move, a wind that comes from vents, seasons defined by whatever cycles the ship's systems produce, rather than by the orbit of a planet around a star. The developmental psychology of children raised in artificial environments has been studied in the context of space station research, isolated community research, and some more specific theoretical work on generation ships. What the research consistently suggests is that children are remarkably adaptable within their formative environments. They calibrate to what is normal based on what they experience. A child raised on a generation ship will not feel deprived of an open sky in the same acute way that an adult who grew up on Earth and then transferred to a ship would feel it. The ship's environment is simply the world to them, the way that any child's environment is simply the world before they have a basis for comparison. This is both reassuring and somewhat sobering. It means the children will likely cope. It also means they will be genuinely different from their parents, in ways related to their formative experience. The first generation aboard the ship retains its connection to Earth through memory, through lived experience, through the felt knowledge of what an open world is like. The second generation has that connection only through what their parents tell them. The third generation has it only through what their grandparents told their parents, who passed it on. Each step, the signal is a little weaker and a little more mediated. By the fifth or sixth generation, Earth is not a place anyone remembers. It is a concept, a story, an origin myth. What that shift means for motivation, for cultural cohesion, for the psychological relationship to the mission, is genuinely uncertain. It might be fine. The community might have developed its own strong internal identity by then, its own sense of purpose rooted in what it is rather than where it came from. Or the loss of that connection might create a kind of rootlessness, a disorientation about identity that expresses itself as social fragmentation or apathy toward the mission. The design of the ship's culture needs to anticipate this transition, needs to create a sense of identity and purpose for the people who were born on the ship, not just for the ones who remember leaving. Not just the identity of going somewhere, but the identity of being someone worth going there. The health challenges specific to being born and growing up in a closed artificial environment are not trivial. The human immune system develops in part through exposure to diverse microbial environments. Children who grow up in very clean, very controlled environments can develop immune systems that are calibrated differently from those of people raised in contact with the full biological richness of a natural world. The hygiene hypothesis in immunology suggests that some modern immune disorders, certain allergies, some autoimmune conditions may be related to reduced early life microbial exposure. A generation ship, by definition, is a closed environment with a limited and controlled microbial community. The children born there will have immune systems shaped by whatever microbiome the ship contains. This is manageable with careful planning. The ship's biological systems would ideally maintain a diverse and healthy microbial ecosystem, not a sterile environment, but a thoughtfully managed one. But it requires attention. The microbiome of the ship is as much a life support concern as the oxygen content of the air. The musculoskeletal development of children also depends on appropriate gravitational loading during growth. If the ship's artificial gravity is well calibrated to Earth normal, this should not be a serious problem. But any deviation, a lower effective gravity, uneven distribution across the habitat, periods of weightlessness during propulsion phase can affect bone density and muscle development in ways that compound over generations. The first generation might adapt successfully. The second might show some subtle differences. By the fifth generation, if the gravity environment has not been carefully managed, the cumulative effects on the population's physical health could be meaningful. Vision is another area of concern. Human vision develops in response to the visual environment during childhood. Children who spend their formative years in environments with limited natural distance vision, limited outdoor time, consistently indoor lighting, at close to moderate ranges, show higher rates of myopia. The architectural design of the ship's habitats and the deliberate creation of spaces with sufficient visual range to support healthy vision development in children is a genuine medical consideration, not catastrophic, but real, and one of many such considerations that multiplies across generations if not attended to from the start. There are people alive today who think seriously about these problems for a living, not because a generation ship is about to be built, but because the rigorous study of what it would require generates insights that matter for more immediate challenges. The closed ecological systems research, inspired by generation ship concepts, has applications for lunar and Mars habitats. The population genetics work on minimum viable crew sizes informs the design of any long-duration mission, including missions within our own solar system. The psychology research on long-duration, isolation, and confinement is directly applicable to the year-long and multi-year missions that space agencies are actively planning to Mars, beyond. The governance frameworks being developed for theoretically autonomous communities in deep space have implications for any future settlement that must function independently of Earth oversight. The generation ship, in this sense, is not just a science fiction concept waiting for the far future. It is an intellectual forcing function, a way of asking questions hard enough that the answers are useful even before the question becomes practical. NASA and ESA have both sponsored research into the human factors of long-duration space missions. The one-year mission, in which astronaut Scott Kelly and cosmonaut Mikhail Kornienko spent 340 days aboard the International Space Station in 2015 and 2016, was in part designed to study the effects of extended space habitation on the human body and mind. The findings were significant. Both astronauts showed measurable changes in vision, immune function, gut microbiome composition, gene expression, and cognitive performance over the course of the year. Scott Kelly's twin brother Mark Kelly, also an astronaut but not aboard the station, served as a control subject for the biological comparisons. The results pointed clearly to the need for much deeper understanding of long-duration human spaceflight before any mission of multi-year or multi-decade duration could be undertaken safely. A generation ship at even the most optimistic timescale involves not 1 year in space, but decades or centuries. The scale of the biological challenge is categorically different. Some generation ship concepts address the psychological problem at the architectural level. If the core issue is that people live in a closed metal environment with no natural world, no real sky, no weather, no open space, then build the sky into the ship. O'Neill's cylinders, proposed by physicist Gerard K. O'Neill in the 1970s, are large rotating habitat structures. The rotation creates a centrifugal acceleration that functions as artificial gravity on the inner surface. With a large enough cylinder, several miles in length, perhaps a mile or more in diameter, you can fit an actual landscape inside. Not a simulation. Not a display screen showing a sky. A real terrain, with soil, trees, bodies of water, atmospheric circulation, actual weather produced by the management systems of the cylinder itself. You can have something that looks and feels like a sky, curved in the way the cylinder curves, but genuinely open rather than a ceiling a few feet above your head. You can have open spaces large enough that you cannot immediately see the walls. The psychological difference between living in a pressurized corridor and living in a space large enough to feel like a real landscape would be profound and very likely important for maintaining mental health across the generations of the voyage. Whether it is sufficient to prevent all the long-term psychological effects of knowing the sky is a machine, knowing you cannot leave, knowing your whole world is a vessel hurtling through the dark, is an open question. But it addresses the most visceral and immediate elements of the confinement problem. Rotating habitat designs also solve the gravity problem directly. Humans in zero gravity or very low gravity lose bone density, muscle mass, and cardiovascular function over time. The immune system is affected. Fluid distribution in the body changes in ways that cause problems across years and decades of exposure. Long-term weightlessness is incompatible with maintaining a healthy population across multiple generations. A rotating cylinder provides constant centrifugal acceleration that the body experiences as gravity. It is not identical to planetary gravity in every detail, but for large cylinder radii the differences become small enough to be biologically irrelevant. The children, born on a generation ship, raised in its environment, socialized within its culture, trained in its technical demands, they will be different from the people who launched it. Not in a dramatic sense, not transformed into something unrecognizable, but genuinely different in ways that environments reliably produce in human beings. Their bodies will be calibrated to the ship's gravity, its atmospheric composition, its light cycles, its microbial environment. Their psychology will reflect never having experienced wilderness, never having been alone in any meaningful sense, never having encountered a natural world that operates by processes outside any human control. Their values and intuitions will reflect what their community has taught about what matters and what does not. The founders of the mission cannot fully predict what that person will be like, 7 or 10 generations removed from the launch. They can try to design for it. They can build institutions and culture and physical spaces that they believe will produce healthy, capable, mission-oriented people. But human development is not engineering. It is biology, interacting with culture, interacting with individual variation, producing outcomes that are always somewhat surprising. After 10 generations, the population of a generation ship will be genuinely unprecedented in human history. People shaped by circumstances no human being has ever faced before. There is something important to sit with in that. The decision to launch a generation ship is a decision to create people who had no say in being created under those circumstances, who will live and work and love and eventually be gone within the walls of a vessel they did not choose. This is not unique to generation ships. Exactly, every generation is born into circumstances not of its choosing. But the generation ship version is more deliberate, more total, more final. You are making choices for people who do not exist yet, choosing their entire world for them before they are born, with the understanding that it is the only world they will ever have. That is the weight that every generation ship proposal eventually has to reckon with. Not as an argument against doing it, necessarily, but as a thing that requires honesty. Before we get to the children, there is an entire dimension of the generation ship problem that rarely gets enough attention: manufacturing. A generation ship is, at its core, a machine, a very large and very complex machine. And machines break. Not just the reactors and the life support. Everything. The pumps in the water recycling system. The electric motors in the agricultural systems. The seals in the pressurized compartments. The bearings in the rotating habitat sections. The filtration membranes in the water processors. The circuit boards in the control systems. The lighting systems. The medical equipment. the fabrication tools themselves. Every component on the ship has a finite service life, and when that service life ends, the component has to be replaced. For the first decade of the voyage, the ship carries spares. For decades 2 through 5, the ship uses those spares and manufactures new ones using onboard fabrication capability. But eventually, the fabrication equipment itself wears out, and the materials it uses are consumed. And the knowledge of how to repair the fabrication equipment has to be maintained alongside the knowledge of how to use it. A generation ship without comprehensive manufacturing capability is a generation ship on a deadline. It is using up its resources without replenishing them. Sooner or later, and on a multi-century voyage, sooner or later is a certainty. A critical component will fail, and no spare will exist, and the manufacturing equipment will be needed. If that equipment is functional, and the people operating it understand what they need to make, the crisis is manageable. If either of those conditions is not met, the crisis becomes something worse. The manufacturing requirements are themselves an entire engineering program: metalworking, polymer synthesis and processing, electronics fabrication, glass and ceramic production, biological material production for medical applications, textile production for suits and seals and filtration materials. The ship needs to be, in a meaningful sense, a small industrial civilization, not dependent on any external supply chain, not relying on components that cannot be reproduced. And the people running that industrial capability need to understand it at the level of principle, not just procedure. They need to know why the metallurgical process produces the result it does, not just the steps to follow. Because the day will come when the steps as written do not quite match the situation, and someone will need to reason from first principles. This is yet another place where knowledge depth across generations is the critical variable. The manufacturing knowledge, the industrial knowledge, the engineering knowledge, all of it has to be as alive in Generation 7 as it was in Generation 1. Not preserved in books alone, but practiced, taught by doing, maintained as living skills rather than archived procedures. The legal and ethical framework of a generation ship is something that civilization theorists have been exploring with increasing seriousness. Because a generation ship creates conditions for which no existing legal framework was designed. The people aboard are citizens of the mission, not citizens of any Earth nation in any practical sense, because their connection to Earth nations dissolves across the distance and the time. The laws of the countries that funded and launched the mission have no enforcement mechanism beyond the hull. The ship's own governance structure is the only operative authority. This means the generation ship has to develop, from the beginning, a complete legal system. Not just rules about behavior, but frameworks for rights, obligations, property, contract, harm, and justice that can function in its specific context. Property on a generation ship is a particularly interesting problem. In most legal systems, property rights are ultimately backed by some state apparatus that can enforce them. On a generation ship, the enforcement capacity is entirely internal. The community has to believe in and enforce property rights through its own institutions. And the nature of property on a ship is different from property on Earth. Everything aboard is in some sense shared: the air everyone breathes, the water everyone drinks, the agricultural systems everyone's food comes from. But individual ownership of things, personal possessions, creative work, perhaps housing units, has to be defined and protected if people are to feel any sense of personal autonomy. Getting this balance right is not trivial. A system too communal feels oppressive. A system too individualistic creates inequalities that, in a closed environment, become sources of resentment without escape. The legal framework has to find the right balance for the specific conditions of the ship, and it has to be flexible enough to evolve as those conditions change across centuries. The treatment of serious wrongdoing is another area with no easy answers. On Earth, one response to people who harm others or violate community norms is incarceration, removing them from the community for a period of time. On a generation ship, where every person is a resource and space is limited, long-term incarceration is wasteful at best and destabilizing at worst. And there is nowhere to exile anyone to. You cannot banish someone from the ship without putting them outside in space, which is not a proportionate response to most forms of wrongdoing. The generation ship legal system has to find ways to address harm, maintain accountability, and protect the community that do not rely on mechanisms that only work when the outside world is accessible. Restorative justice frameworks, intensive community-based rehabilitation, the careful management of people who are dangerous without the option of simply removing them. All of these are areas that require serious advanced thinking and institutionalization, not crisis management. Designed systems, built in from the start. There are historical analogies for some aspects of what a generation ship community would face, though none of them match perfectly. Island communities that developed independently over centuries show something of what cultural isolation does to human groups over long time periods. Populations that colonized Pacific Islands thousands of years ago developed distinct cultures, languages, and technologies from a common ancestral base. Separated from each other and from their origins by ocean distances, they became genuinely different peoples, sharing deep roots, but expressing those roots in very different ways. A generation ship would produce something similar. Not a divergence from other ships, necessarily, but a divergence from Earth itself. A new culture, rooted in the culture of the founding community, but evolved by the specific pressures and conditions of the voyage. The early colonial expeditions to the Americas offer another, partial parallel. Small communities cut off from their home societies, having to be self-sufficient in ways their culture had not previously required, under conditions of genuine stress and uncertainty. These communities made it, when they made it, through a combination of adaptive problem-solving, social cohesion, and enough luck that the crises they could not handle did not arrive at the wrong times. They also, frequently, did not make it. The historical record of colonial ventures is full of communities that collapsed. Roanoke vanished without explanation. Many early settlements along the Atlantic coast failed before enough knowledge had been accumulated about how to survive in the new conditions. The generation ship is orders of magnitude more demanding than any terrestrial colonial venture. The conditions are more extreme. The isolation is more complete. The duration is longer. The inability to receive emergency resupply from outside is more absolute. History suggests that the communities that survive under these kinds of conditions are the ones that adapt their culture to their circumstances while preserving the core competencies they cannot afford to lose. Not the ones that insist on doing things exactly as they were done before, regardless of changing conditions. But also not the ones that lose their technical foundations while adapting the social surface. Both kinds of failure are real. Both can be the end. The emotional weight of all of this is worth acknowledging directly. A generation ship is not just an engineering project. It is a human story of extraordinary dimensions. The people who board it are making a choice that no human being has ever made before. They are choosing to leave not just their country or their continent, but their entire world. Every person they have ever known, except the ones also boarding the ship, will be left behind. Every place they have ever been. Every landscape they have ever loved. The sky they have looked at their whole lives. The seasons they grew up with. The smell of rain and grass and ocean. None of it comes with them. And they know, on the day they board, that they will never see any of it again. That is a grief that does not have good comparison in human experience. The closest thing is emigration from a place one loves deeply, knowing the return is impossible. But even that comparison falls short, because the immigrant can at least look at the same sun, breathe air that has moved across the same planet, hear news from the place they came from. The generation ship passenger loses the sun, loses the sky, loses the connection in a way that is far more total. And yet, people would board. People do choose extraordinary sacrifices when they believe in the thing they are sacrificing for. The founders of difficult colonies, the people who committed themselves to long and dangerous expeditions, the individuals throughout history who traded the familiar and the safe for the chance to be part of something that felt larger than a single life they existed in every era. The generation ship would attract exactly those people. People for whom the prospect of being the beginning of humanity's first interstellar civilization outweighs the profound cost of what they are giving up. People who find meaning, not in the familiar and the safe, but in the frontier, the unknown, the chance to go somewhere no one has ever been. And their children would inherit not just the ship, but the choice their parents made. Would grow up in a community shaped by that choice, by the culture of people who believed strongly enough in something to give up everything ordinary for it. That is not nothing. That cultural inheritance, the ethos of people who committed to the impossible, might be one of the most important things the founders could leave for the generations that follow. The question of which star to aim for is one that has exercised astronomers and space mission planners extensively. Proxima Centauri. B. The planet confirmed in 2016, orbiting within Proxima Centauri's habitable zone, is the most discussed candidate. But Proxima Centauri is a red dwarf star. Red dwarfs are very common. They make up roughly 75% of all stars in our galaxy. They are long-lived, burning their hydrogen fuel for trillions of years. But they have characteristics that make their habitable zone planets challenging. Red dwarfs are prone to intense stellar flares, energetic eruptions that blast their nearby planets with radiation. Planets in the habitable zone of a red dwarf are so close to the star that they are likely tidally locked, one face permanently toward the star and one permanently away. This creates extreme temperature differentials and unusual atmospheric dynamics. Whether life could exist on such a planet is genuinely unknown. Whether a generation ship crew could live on such a planet is an additional question. Tau Ceti is more appealing in some ways. It is a sun-like star, similar enough to our own star that its habitable zone planets would experience something closer to Earth-like conditions. It has a confirmed planetary system, though the confirmed planets are larger than Earth and may not be the most promising targets. But at nearly 12 light-years distance, it represents a more demanding journey. Further destinations in the galaxy's more sun-like star population require correspondingly longer voyages. The choice of destination, is not just an astronomical decision. It is a decision about how long the voyage will be, what the destination conditions will be like, and therefore what the ship needs to prepare for at the receiving end. A poorly chosen destination, one that turns out to be less viable than hoped, or that requires additional capabilities the ship does not have, could mean arriving somewhere that cannot support the community that has just crossed the void to get there. The reconnaissance work done before launch, using the most powerful telescopes available, is as important as the engineering work on the ship itself. Because the best engineered ship in history, arriving at a destination that cannot support a human community, has delivered its passengers somewhere they cannot survive. The question posed by the title is not answered purely by engineering. And before the final reckoning, it is worth stepping back for a moment to appreciate the full scope of what we have covered. We have talked about reactors that must run for centuries and be maintained by people who were not alive when they were built. We have talked about biological life support systems that must function as complete ecosystems, not just machines, and that must be understood by a population that has no university departments to consult. We have talked about genetics and population size, and the quiet, slow-motion threat of genetic bottlenecks that accumulate invisibly across generations until the damage surfaces in fertility. Statistics. We have talked about food production systems that have to absorb failure without cascading, water recycling that has to work continuously for centuries, medical systems that have to cover everything without any outside specialist care. We have talked about the psychological reality of living one's entire life in a closed world, of growing up without sky or wind or anything wild, of knowing that you cannot leave, of the frictional pressure that builds in communities where the only option is to stay. We have talked about governance, the hardest problem of all, perhaps, and how you write a social contract that is legitimate for people who were never asked to sign it. We have talked about knowledge, about the fact that information in a database is not the same as understanding in a trained mind, about cultural transmission, fidelity, about the slow, quiet disaster of expertise, degrading across generations until critical systems are operated by people who follow procedures without understanding principles. We have talked about manufacturing and legal systems and historical analogies and the emotional weight of what it means to board a ship you will never disembark for as long as you live. All of this is the generation ship, not just the spacecraft, the civilization inside it. And the civilization is the harder engineering problem. It is not just about whether the reactors can keep running or whether the air recycling stays functional. It is about whether human civilization, a small, isolated, centuries-long slice of it, can survive the weight of its own situation. Whether people can maintain the fragile web of trust, competence, and shared purpose that separates a functioning society from one that is slowly coming apart. Whether the meaning of the mission survives the centuries between departure and arrival. Whether the people who finally reach the destination, looking at a new world through forward cameras after a journey their ancestors began, are still the inheritors of something worth carrying across the dark. The honest answer, based on everything we know about biology and psychology and social dynamics and engineering and history, is maybe, under very specific conditions. With extraordinary design care, extraordinary governance, extraordinary luck, and a founding culture that somehow manages to bequeath its successors not just the ship and the knowledge, but the will to use both. It is possible, not guaranteed. Not even necessarily likely without those conditions all being met. but possible. And in the context of interstellar travel, possible is actually a significant word. Because everything that makes the stars accessible at all is barely possible. The energy requirements, the materials, science, the biological systems, the centuries of human endurance, all of it sitting right at the edge of what can be conceived of and done. And here's a thought worth sitting with as we near the end. In a strange and beautiful way, we are all already aboard a generation ship. Earth itself is a sealed world, drifting through the dark, carrying everything we need to survive, locked inside a thin shell of air and water and rock. Our ecosystems recycle our air and water. Our sun provides the energy. Generations are born, live, and move on, each one inheriting a world they didn't make and handing it forward to those who come next. We have no resupply ship. We have no rescue mission. If we break our life support, if we poison our air or exhaust our resources, there is no outside and no help. The lessons of the generation ship are, in the deepest sense, the lessons of living on Earth. The generation ship is not a comfortable concept. It does not let you feel easy about human ambition the way a faster solution would. It is slower and harder, and it raises harder moral questions than almost anything we have ever attempted. It asks more of people across more time than almost anything we have ever asked of people before. But it is also, in a deep sense, more authentically human. It is people choosing to carry themselves forward across an impossible distance, using nothing but what they can build and what they can be, and what they can pass on to the children who come after them. No shortcuts. No trick of physics that dissolves the hard part. Just a ship, a direction, and the accumulated knowledge and culture and biology of a small community moving through the dark at a fraction of the speed of light, across the years and the generations, towards something they were told they would find on the other side. The stars are 25 trillion miles away. And the hardest distance in that journey is not the physical one. It is the distance between what we want to be and what we actually are. That is the distance a generation ship has to close. And if we ever get the physics and the engineering right, the real question, the one that will determine whether anyone arrives, is whether we can close that one too. Good night.